Yeah, I can't remember if I started doing these or not, but essentially you've got to either get these logs into one equation on one side, or some of them are just simply easy to solve. Now, keep in mind that ln is simply a log to base e. Ln is simply a log to base e. So that means something like this is just saying you just got to rearrange it in exponential terms. So ln is a log. So if I change this to log, and they just want to use ln to say that it's a log base e. So what this is saying is e to the minus 3 is equal to x, or e to the minus 3 means 1 over e to the 3 is equal to x. So you could either punch that into your calculator and come up with x, or your teacher might just want it like that. This one as well, and when you look at it as log, so when they just say log, it's base 10. So all they're saying here is that 10 to the power of 2 is equal to whatever's in that bracket, 3x minus 2. So that's 100. And then we bring the 2 to the other side. 100 plus 2 is equal to 3x. And then you divide both sides by 3. So x is equal to 102 divided by 3, whatever that is. I think it is 34. And then this one, the secret here is knowing your rules of logs. So first of all, this is x squared. Bring the 2 here. Then you can bring, well, you can convert this one first if you want. So when you're adding two logs like this, it's really the same as the log of 2 times that. So you got 6x minus 8. So really that's log of 6x minus 8. And then when you bring it to the other side, remember that this is squared now. You've got log x squared minus log of 6x minus 8. That's the same as finding the log x squared. And now it's equal to 0, by the way. That now equal to this. So it's just a rule of logs that when they're added or subtracted logs with the same base, you're allowed to rewrite them like this. And this is just simply saying 10 to the 0 is equal to this. Well, 10 to the 0 is 1. So if we get rid of the log and rewrite it in exponential form, 10 to the 0 becomes 1. Then you multiply both sides by this denominator. And you subtract it all to this side. It's all equal to 0. And this is just going to be, and I think I did this one, this is just going to be a factoring. So we're looking at minus 2, no, plus 4, no, minus, I forget what we're, yeah, this is minus now. Whatever it is, it's like plus 4 minus, it's got a factor. So don't, like, just figure it out. So what's 4 and 2, 8 and 1. I might have done a number thing there. You might need the quadratic, but anyway, I'm sure it's factorable. I just might have rewritten them. They're all like this. So this becomes x times this. So it becomes x squared minus x. And when you bring the minus 4x over here, it becomes divided by 4x. And then it's simply asking what is 10 to the 0 equal to this. 10 to the 0 is equal to 1. You do the same thing. Same with that. When it's equal to a number here, what you simply do is you rewrite this now. They're both log base 3. So that's the same as saying this. And now since it's 3, that's the same as saying 3 to the 3, which is 9. Because you bring this 3 to the 3 is equal to whatever's in here. So 9 is equal to this fraction. And then you simply multiply both sides by the denominator to get it. And remember that you've got to distribute this 9 into the bracket. So it becomes 9x minus 9 is equal to that. And then you get all your x's on this side and all your, and it ends up being 34 is equal to 8x. Something like that. Mike got the math wrong, but it doesn't matter. They're all doing this, the same thing. This is the same as when it's added, it's multiplied. So this times this times this is going to become a quadratic, and then it becomes 9 to the 1. So it's all going to be equal to 9. Then you expand it, get it all to one side, and solve it like a factoring question. So they're all like that. There's nothing really challenging on this page. So we'll go to the next one. prove the following. This is a little bit more difficult. I think I did all those actually. Yeah, I did all this. Oh yeah, this is where I stopped. So where I got stuck stupidly is here. There's no reason to be stuck here because that 1.1 is simply 3 divided by 2. And when it's divided, it's simply log 3 minus log 2. What they're trying to do here, I think, is getting you used to replacing it. Well, according to our legend there in the bottom, log 3 is equal to y. So I can just replace it with y, and log 2 is equal to x. So you get y minus x is what this equation is equivalent to. So again, just used to fiddling with numbers. Well, 200 is 2 times 100. I think I did that one. So really, we're talking about log 2 plus log 100. Log 100, 10 to the 2 is equal to 100. So that's 2. And log 2, we've learned, is equal to x. So we'll just do this. So I'll do the harder ones. This 600 here, 6,000 here, which had me stuck for no good reason, is the same as 6 times 1,000. So on the top, you have 6 times 1,000 on the top, and divide by. So well, let's start with what this is equivalent to. This is equivalent to log 6,000 minus log 7. But 6,000 is the same as 6 times 1,000. And that's 6 is equal to 2 times 3 times 1,000. So that can be broken down as log 2 plus log 3 plus log 1,000. What's log 1,000 on your calculator? 10 to the power 3 is equal to 1,000. Minus log 7. So if I look at my equivalence tables, we're talking about log 2 is x. So x plus y plus 3 minus z is what they're talking about. And 10.5, it's probably something that's like 21 divided by 2. Yeah, there you go. Log 10.5 is the same as 21 divided by 2. Well, 21 can be we can rewrite that as log 21 minus log 2. And we can rewrite log 21 as 7 times 3. Which means I can rewrite it as log 7 plus log 3, and then you just replace everything based on your legend. Log 15 is easy. It's 3 times 5, but we don't have the 5, so 30 divided by 2. 30 divided by 2 is 3 times 10, yeah. Log 15 looks like it's easy, but really it is log 30 divided by 2, which becomes log 30 minus log 2, and log 30 can be broken down as log 30 3 times 10, so it can be broken down as log 3 plus log 10. Log 10, 10 to the power of 1 is equal to 10, and then you just replace it by your legend. So that's all that is. These, you have to get all your numbers to the right side. To get all these numbers to the right side. So 3 to the power of x is equal to 14. You have to take a log of 3 to the power of x is equal to 14, and then that should be to the power of x, and then you're allowed to put x down here, which means x is equal to 14 divided by log 3. Remember that logs of numbers are just like a number. It's just like a number. So you can move it down, you can move it around like it says 3x. Okay. Next one's the same. You have to take a log of both sides, and you get this, which means 1 minus x is equal to log 3 divided by log 2. And you add an x to both sides and subtract that, so you can just get this. This minus this is equal to x. I'm sure your teacher just wants it simplified like this, because that's what we call numerically accurate. And then if I break it down into decimals, it's anything with the decimals no longer accurate. This one, you just take log of both sides, power of x and log of 5. Power of x, and then of course the rule of log says now I can put the x here and the x plus 1 here. And the secret here is you have to distribute your x through it. So let me make sure. Yeah, I'm pretty sure I can just distribute through it. I get x log plus log 5. X log of 5 plus log 5. Or sorry, plus, what was it? It was x plus 1. Yeah, plus log 5. Okay, and then I believe I can subtract. It's a damn good question, actually. Do I have to divide that first? I think I have to divide it first. No, I don't. To get log. So then I can subtract. Yeah, that's right. Then I subtract both sides x log 5. It's equal to that. Oh, come on. Equal to that. Then I can take an x on the left side out of both of them. Then I can divide both sides by that. So this, divide both sides by that, you get this. And that's the answer. All those 1 minus x are the same. You've got to distribute and then isolate your x and then factor out your x to get your x alone on one side. For instance, this one here, 5 becomes 2x plus 1 times the log of 3 is equal to x minus 2 times the log of 2. When I distributed that through, I get 2x log of 3 plus log of 3. You have to always distribute through pretty much. And this one I get x log of 2, x times log of 2, minus 2 log of 2. Okay, now you have to get all your x's on one side and all your numbers on the other. And remember, just treat logs like numbers. So I can subtract log 3 like this, and I can subtract this from the left side. I get that. From the right side, and therefore the left side. And now on the left side, I can extract, there's a 2x, which is just 2. There's just 2 times x. So I can extract an x from both. And I'm left with 2 log 3 minus log 2 is equal to this on the right. And then you divide by this entire number here. This is just, since it's all numbers and there's no x's in it, you can divide by it. That's what you get. This next one is interesting because you have to, you cannot take the log the way it is. Or sorry, 8. I'm going to skip 5. 5's the same. You just get 12. You get 12 to the right side. Actually, these might be a little bit harder. Because you cannot take the log like that. You can't take a log where they're both together. So what's the trick here? It's interesting. 5 to the power of 2x minus 5x is equal to 12. I'm pretty sure I got to get the number. Oh, I know what it is. Sorry. So you can do this. 5 to the 2x is the same as 5 squared to the power of x. So it's just 25 to the power of x minus 5. Yeah. So you're allowed to do just 5 squared. 5 to the square. Gosh. X. Like that. And you're allowed to rearrange them. You can put the 2 here and the x here. Well, 5 squared is just 25 to the power of x. Minus 5 to the power of x is equal to 12. And let's see, what can I do here? I have something minus something. Let's see if this is a true. Just hang on a moment. Yeah, my mistake. That is the method. So you replace, the only thing you don't do is do the 25 to the 5. So you do 5, it becomes 5 to the x squared minus 5x minus 12. And then they like using u. Obviously, if we let x equal 5x squared, it's a little confusing. So you simply let u is equal to 5 to the power of x. So a letter u is the one we're going to use. And keep in mind, if you want to see where that exists, you just put brackets everywhere you see 5x. So we're going to replace that with u. So we get u instead of 5 to the x. We're replacing all 5 to the x minus u. So it's u squared minus u minus 12. And that simply comes down to u plus 4. Sorry, u minus 4. Factoring. And u plus 3. That means u is equal to 4. It's all equal to 0. So u is equal to 4. Or u is equal to minus 3. Now you replace it with your, now you go back and replace u with what it was, 5 to the power of x, 5 with the power of x, like this, wherever you see u. Okay, we'll just even get rid of that or. There we go. And you just say, okay, well, if I take a log of both sides now, I can solve it. So this becomes log, let's see, what power is that? So you take log 5 of x to the power of x is equal to 4, and that becomes x times log 4 is equal to 4. So x is equal to 4 divided by log 5. So that works. And this is the one that doesn't work. When I take both sides, it becomes x is equal to minus 3. Oh, sorry. Because I took log of both sides, it's log 4. There we go. Log minus 3 divided by log of 5. And this one doesn't work because you can't have a result that's negative. I think I did that one too. E is the same thing. You just make the square above e to the x. You take a ln of also, you let u is equal to e to the x. So you get u squared minus 2u minus 15 is equal to 0. So you're talking about u minus 5u plus 3. And that means u is equal to 5, which is probably a possible solution. And u is equal to minus 3, which is not. And then you bring it back. E to the x. This time when you're using e, you're going to use a ln. So it's equal to ln 5 or ln minus, there should be minus 3 over here. Minus 3. Doesn't matter. Minus 3. This one you're taking a ln, because when you take a ln of e to the power of x, the e comes here. But ln of e is simply 1. So you get this. So it's either ln 5, x is equal to ln 5. And actually this works for maybe both of them. So x is equal to, and replace it back. So it's either 5 squared like that equals, so you got e to the x is equal to that. Yeah. Or e to the x is equal to minus 3. And that one's the one that doesn't work because you can't take a ln of minus 3. Okay, that's those. Draw the graph of each of the following logs. Okay, so this is just log base 10, which is the inverse of x, 10 to the power of x. So the two main points on it will be 1, 0, and then 10, 1. And then you can just draw it like a normal log. So logs hug vertically. They go through those points, and then they go off like that. This one simply here is log of minus x. So the negative applies to x. So after drawing your first one, negative is a reflection in the y-axis when it's by the x. Well, this is the y-axis. So this one, this b, number 2, will go like this. And go through the same points, but this time the points have, the x values are negative instead of this. This is a reflection in the x-axis. So the thing will do the reverse like that. And then we also have a translation to the right by 3. So it will now go like that. And you can use Desmos to confirm. This one's, you multiply all your y values by negative 2. You have to rearrange this. This is actually negative x plus 3, and this is not correctly translated. You cannot have a negative number in front of x, so you have to take negative 1 factored out, and you get x minus 3. So it's actually not translated in the direction you thought. It's a reflection in the y-axis, a reflection in the x-axis. All your y values are multiplied by 2, and all your x values, you would, after multiplying it by minus 1, you would add 3. This one's correctly factored. You have a reflection in the x-axis. Multiply all your y values by minus 1. subtract 1 from all your x values. This reflection in the x-axis will make it upside down. So it'll still be that domain. That is not a compression, that's a stretch by a factor of 2. So multiply all your x values by 2 and subtract 3. And then multiply all your y values by 2. There are no reflections, so it's going to look like the black one. It's just going to move 3 to the left, so it'll be here. This one is not factored correctly. You take the 2 out, you get x plus 2. So multiply all your x values by 2, all your y values stay the same, and then subtract 2. So this whole thing will, no reflection, will also be over here by 2. This one's a reflection in the x-axis, so it's going to be upside down. And this negative eventually will be a reflection in the y-axis, so it's going to go like that. If it's not factored correctly, you have to take minus 3 out of it. It becomes x minus 2. So the whole thing's going to go to the right. So after it first goes upside down and then reflects this way, it's going to go to the right. It's going to be somewhere over here like that. Multiply all your y values by minus 3 and then, sorry, all your x values by minus 3 and then add 2 and multiply all your y values by negative 2. It's always smart to do a translation. Okay, this one's a repeat of that one. And these are the word puzzles. So let's have a look at them. This value of the new minivan drops by 40%. Here's how you can look at that. Whatever your original value is, it's going to be times 101, which represents 100%, minus 40%. Well, 40% is 40 over 100, or 4 over 100, or 4 over 10, rather. 1 represents 10 over 10. 10 over 10 minus 4 over 10 is 6 over 10. So really what happens is whatever your object is, it goes to 60% of value. That's what losing 40% is. It's maintaining 60%. And 60% is written as 60 over 100 or 6 over 10, or more likely this. So that is your decay. So since the exponential rate of, and it told us, I think it decays 2% after that. So the first year, your original price, which was $35,000, will decay that much. And then it's telling us it goes down by 2% after that. So it's then going to be multiplied by a value that represents 2%. Well, 1 minus 2 over 100 represents 98 over 100, which represents the fraction or the decimal this much. Now, we don't know how many times that's going to go. So that's the number of years. And I said minus t minus 1 is more accurate because this is the first year. And this is every year after. So you should really put it to t to the minus 1 because on the first year, this doesn't count, right? When t is 1, 1 minus 1 is 0. So it's only this one that matters. And t2, year 2, t minus 1 is just 1, which makes sense because this would only be applied once in 2 years after this first year. So it should really be t to the minus 1. Now they're asking us when is it less than 10,000. So we're just going to make it equal to 10,000. And then we'll know any time after that it will be less. So here's your equation. A little bit of an annoying, tricky question here. So our first step, because this is multiplying this, we could technically multiply this out 0.6 times because it's just a number at this point. So we do 0.6 times that. So we know in the first year, your van, or whatever it is, goes down to 21,000. This is really just 21,000. So we can just divide both sides by 21,000. Well, these simply nullify. So I get 10 over 21 is equal to that. And I think I've done this one already. So log of both sides of log 10 over 21 is equal to the log of this. And that means I can take t minus 1 and just put it down in front. And when I expand that, actually I don't have to expand that. I can just divide both sides by this. And then add 1. And that equation there will tell me the year precisely, because I've subtracted 1, that it loses 10,000. Anytime after this time that I find Well, so you take log 10 over 21 and you got to divide it by log 0.98 and then add 1 after. This is a separate fraction on the left. Okay, word puzzles. A crab fossil contains, yeah, we discussed this. So for this case, because it's every 5,370 years, the fraction over above has to be time divided that, because think of that. If time is 5370, this fraction becomes 1, and that's when it will halve after 53 years. We also know it's a half-life. They've told us a half-life. So we know the base to this is going to be the fraction a half. It's going to be a half to the power of time divided by that. And we also know that it was 100% initially, right? It was 100%, so we'll just call that 100. And they want to know, when is this going to be equal to 38.6%? We don't need a percent. We can just say, and if you don't want to use it, if it bugs you to use the actual numbers, you can just say this is the actual percent in decimal form, and 100% represents 1. So their question is, when is t? And since 1 times anything, it's just that. This is actually easier. So now I take the log of both sides. Log of 0.5, essentially. And log of the right side. Which allows me to take this exponent, the rule of logs, out front. Divide both sides by this number. And multiply it by the other one, which is essentially multiplying by the reciprocal. Doesn't matter where you put this number, but since we usually like to see numbers in the front, we'll do it like this. So that means your answer is going to be, when does this happen? It happens when it's this log divided by this log times that number. And that will tell you the number of years that when this happens. The Trimark has a track record of 4.2 growth. What is the doubling period for this investment? So when does it double? Is what it's going to say. So you can say this. You can just use this value. So final value is equal to initial value times 1 plus 4.2%, right? Which is 4.2 over 100. That's what percent means. And then when I add this over here, this 1 represents 100 over 100. Why 1? Because it's total value plus its growth, or total value minus its growth, minus its decay. So this becomes, obviously, 100 over 100 plus 4.2 over 100 becomes 104.2 over 100. And in decimal form, we simply move the decimal over 2. So it's 1.42 is the decimal. And that's going to be to the power of, when does that happen? After many of years. But they want to know when it's doubled. So what we can say is, if it's doubled, the initial can be 1. And what's double 1? 2. That's the easiest way to do it. So our first step is divide both sides by this number. That's very easy. Take a log of both sides now. Now you're allowed to put t in front of the exponent. You're always allowed to put an exponent of a single log in front. Divide both sides by this number, because a log of any number is just a number. So you can treat it like a number. And that will be your answer. At log 2 divided log 0.104 times 2, that'll give you the number of years for this mutual fund to double. This helps patients stop smoking by chewing gum. Each gum introduces a certain amount of nicotine. Nicotine has a half-life of 3 hours. Patient will feel the urge to smoke when the level of nicotine drops below 0.45. So what does that mean? It means in 3 hours, this halves. In 3 hours, this halves. It would become 0.75 after 1 hour. And it would become what's half of that? 0.325. Well, anything before 4.5 is an urge to smoke. So we have to find when this happens. Somewhere in between here, right? She chewed the gum at 8 a.m. and another at 10 a.m. Okay, so she gets it. what time will she feel the urge to smoke? So we know after 2 hours, there's 1 hour, 2 hours, kind of cheating because she has an urge to smoke at 9:45. It's kind of cheating. So we should first look at those first 2 hours. 8 to 10 is 2 hours, isn't it? So we know that final amount of nicotine is equal to initial amount of nicotine. And they tell us it's a half-life, so the base is a half. And they tell us it's every 3 hours. So we have to do time divided by 3 hours because that means, oh, every 3 hours. So she's going to make it past 10 a.m. So that means she is indeed at 3 hours, it will halve. So every 3 hours it halves. So this T over 3 creates a halving every 3 hours, which is what we want. So now we know that she has this going for 2 hours, right? So she first takes a full amount, 4.5, sorry, of 1.5 milligrams. And she does that for 2 hours before she takes another 1.5. So there's still some in her system before she takes that second gum at 10 a.m. Well, what happens in the first dose? The first dose, 2 hours passes. So we should figure out how much is in her system after 2 hours. It's a half to the power of 2/3 times 1.5, right? Because the dose hasn't worn out yet. So we always take the exponents first because of bed mass. So you do the exponent of 2 over 3. We're going to do it in brackets. 2. If you don't do it in brackets, it might do the exponent of just the 2. 2 divided by 3. Because that's the first 2 hours. Close brackets. And hit equals. Well, we also now have to multiply it by the number of milligrams. So she still has this amount in her system when it happens. So we can either add that as a number, but at 10 a.m., she has this much in her system. Let's just call it 5. When she adds another 1.5 milligrams. So that's going to be equal to this. At 10 a.m., this is what she has in her system. And we need to know when that comes down to 0.45 when she has the urge. So that means her final amount is going to be equal now to this same half-life formula we started with. T divided by 3. But she starts fresh at 10 a.m. She starts fresh with that new dose at 10 a.m. This is part here is in her system. It's locked in. And actually, that's going to decay as well, isn't it? Will it decay? Or does it get a boost? That's interesting. Does this initial one decay as well? Or is it just considered an amount? But it's still half-lifing. So yeah, maybe that we've got to do it twice. This is a damn interesting question, actually. I'm going to have to just take some time and get back to you. Is the last one on this page? No. Oh, the pH for this is, since it's hydronium, we know it's just the negative log of 0.01 and the negative log of 1.5 times 10 to the negative 10. So you take the log of those numbers and then change the negatives. You multiply by -1, so you change the negative sign. This, by the way, is same as 1 times 10 to the negative 3, which is 10 to the negative 3. So I know the log of that is going to be negative 3. And when I multiply that by -1, I get 3. So the pH of that is 3. The other one's a little bit trickier. It's going to be somewhere between 10 and 11, I think. So I'm going to get back to this one. That's an interesting one. I think I have to keep having life this based on the initial time. And then I have to half-life this based on this equation, T over 3, but subtract the first 2 hours because they didn't take that until hour 2, just the way we did with the minivan. But I'll confirm with you before I put it on video. Yeah, so it's as I thought. So the first dose is taken right away, and then you've got to add a second dose that has the same half-life and has the same half-life time period. But this one you have to subtract. It has to be t. So at the top it has to be t minus 2 over 3. And of course, t cannot be, actually that doesn't work for, and you have to put a restriction on the domain here when t is bigger or equal to 0. Because if this was, sorry, bigger or equal to 2 on this one, because if t was 0, this would create a minus exponent and create a weird thing. So this is only valid when t is bigger than 0. Now, but what's strange about this one is because there's two exponents with t, I don't think we can solve it with log. So again, they can both be divided by 1.5, but they cannot be added. This is a very interesting one. Let me just think a bit more. Yeah, okay, I got it. So what you have to do is say, okay, well, we're going to have 2 hours. So the half-life has a half-life of 3 hours. So we have to say, we have to figure out the amount after 2 hours first. So after 2 hours, this t is 2. So we have to do a half to a 2/3. 2/3 is 0.6666666 times the amount. And we discover this is how much the first dose is left. And then the second dose is started, but it has the same half-life. So we can just add the second dose, which is 1.5 milligrams. And we get this total second dose. And we'll just put a 5 there. Now with that one, we can say, okay, that one starts at 10 a.m. So that means 2 hours have already passed, and we have to note that. 2 hours have already passed when we start this formula. And this formula, we don't know how many hours have passed. But if you want to get precise and know the exact hours of, instead of adding 2 at the end, you can subtract 2 here. This will allow for only 2 hours more. But what we're going to do to play safe in case it's less than an hour more, I don't think it is, we're going to do this. We're going to say t, and then we're just going to remember to add 2 hours. I believe if you did this, you'd get more accurate. Okay? So maybe what we'll do is we'll do both scenarios. We'll just do t first. So to solve this, and the question is, when does this become down to this? So when the dose is down to this much, then you have an urge to smoke. So the question is, when does this 2.45 shrink down to this? Obviously, half of this is 1.2 and half of this is 0.6. So it's going to take at least 6 hours more. So yeah, I could have gotten away with the 2t minus 2 here. So our first step is to divide both sides by this. When you do, obviously it cancels on the right side. I'm going to just take that. Well, I'm not even going to bother. Then in brackets, you take the log of both sides, because that's the only way you can get your exponent down. Once you take the log, you can get this exponent down. Remember, it's t divided by 3 because every 3 hours. And then you can divide both sides by that. So now we've got this. That. And then finally, you multiply the entire right side, whatever that comes down to, by 3. Now, I'll show you what would have happened if we'd had the minus 2 there in a second, but let's figure this one out first. We're going to take our 0.45 I'm going to divide it by this. Instead, I'm going to divide this by 0.45 and then flip it. It's the same thing. Flip. And then I'm going to take the log of that. And then I'm going to divide it by the log of 0.5. You get a positive value, and I'm going to multiply it by 3. And I get this. 7 hours. 7 hours. And that's after add 2. That's before I add the 2 hours. So I have to add the 2 hours we didn't have. But had I done the t minus 2, that would have achieved that as well. This assumes 2 hours is unaccounted for. I'd have to add 2 to both sides. And that's the same thing as adding 2 hours that we had in the beginning. So I add 2, and I get 9.325 54 hours, let's say. And that would be 9 hours and whatever 0.32 of 60 minutes is. So I'm going to just subtract 7 off this one. Now, if I multiply by this, I get how many minutes there? There's 19 minutes. 19 minutes. Do something. So I get 9 hours, 19 minutes. Then if I take the fraction off that one, which I just did, and multiply it by 60, I get the seconds, 31.4. So they're over 31. Let's just say 31 seconds, 31.4. So that means after 9 hours, 19 minutes, took the fraction or the decimal remaining and multiplied by 60. And then I took the decimal of that, multiplied by 60 for seconds, and 4.7 seconds, the patient will feel the urge to smoke. This can also be proven by plugging in this decimal into the full equation to see if you get 0.45. Okay, next one. That was a bit challenging, kind of stumped me more from fatigue than anything. We already did that one, so that's good. Go back to this. Just one left. And the one left is like the inequalities. This is actually very simple. Yeah, I think this is a repeat, but in case it isn't, this one you just have to write in exponential form. I think I did this already, so it's 3 to the power of 4 is equal to 81. 7 to the power of 1 is equal to 7. 1/2 to the power of 3 is equal to 1/8. 3 to the power of 0 is equal to 1. 4 to the power of minus 3 is equal to 1 over 64. So the result is always here. The base is always here, and the exponent is always there. 6 to the power of minus 2 is equal to 1 over 36. X to the power of z is equal to y, so that's just a general statement. M to the power of half is equal to n, a general statement. These, you do the same. So this is the result, so it would go here. This is the base, so it would go here. And the exponent goes on the other side of the equal sign. So it's log base 8 of 64 is equal to 2. Log base 10, sorry, log of 10,000 base 10 is equal to 3. Log of base 4 of 1/16 is equal to minus 2. Log base 3 of 181 is equal to minus 4. Log base 1/2 of 32 is equal to minus 5, etc., etc., etc. True or false? So this can be broken down into log x. We'll do these true or false ones. I think I've done this. If not, it's okay. Skip if I have. So this, you just follow the rules of log. So that means this top can be made separate. And then because they're dividing in here, I can subtract them. So it'd be minus this, log of this. And then just keep in mind that this 3 can then come down in front. So it's log x minus 3 log y. So this is true. This one, this can be, this is not true. You cannot break down two things that are minus in the brackets. If these were being divided, a divided b by b, then this would be true. So the correction of this, if you were asked for the correct solution, it would be a divided by b in this bracket. this is true, the k can come by. So this is just training you on the rules of log. The k can come down in front of log exponent. These things are not true. That's not how that works. If anything, it's reversed. It's log of a times b is equal to log of a plus log of b. That is not true. This is not true at all. It's almost true, but it's actually equal to log a. And actually, it's not at all. It would have to be in here like this. Let me see what it said. No, actually, that's not true. This is actually equal to log base b of a. This is what we use when we don't have a variable log key on our calculator. We want to figure out a log that isn't base 10. So if it was log 8 base 2, I'd do log 8 divided by log 2. And it's equal to this. The k can come down in front, so that's good. This is interesting. Whenever you have a ln a to the base a, whatever's the exponent is equal. This is a negative, so it could go up in as an exponent here. And 1 to the x to the negative 1 is equal to x. So indeed, it would be equal to ln x here, which is equal to ln x. This is tough to fathom. To rearrange it, you have to ask what this is asking. This is asking if this square root of x to the power of this is equal to this. It might not seem it at first, except that we can divide these exponents into exponent of an exponent, like that. That's a rule of exponents. And any square root to the square cancels out. So you get x of k is equal to x of k, which is true. Okay, let's see what else there is on this one. Is it? No, a couple more. I think we did those, but anyway. I think we did all these. Doesn't matter. Solve. So this is base 10. So 10 to the negative 3 is 1 over 10 to the 3, which is 3 zeros, which is 0.001. So that's x. Solve 10 to the 2 is equal to this. So this is equal to 100. Add the 2, 102, x is equal to, yeah, I did this, 102 divided by 3. I think we did all of these. So this can be divided. Then you do 9 to the power of 1. Yeah, I did all those. Did these. So this one, you would just put this to the power of that to prove this is true. And it looks difficult. Actually, these last two look pretty hard. So we're going to be proving that this to the power of this is equal to this. Well, is equal to, sorry, just equal to x. Remember that we're allowed to do the square of that. Oh, hang on, let me make sure I got it right. Yeah. That to the power of that is equal to x, is what it's saying. And remember, we can do the square of the square root cancels. And then when you have base to the square root of the log of the base, they cancel. So yes, x is indeed equal to x. This one is saying this thing here, which is a little bit complicated looking, to this power is equal to square root of x. Well, first of all, this can be represented as anything to the denominator can be represented as a negative 1. So we can say the negative 1s times the negative 1 cancel. However, for these to cancel, I would have needed a 2 in here for the square root to cancel, for the log b square root to cancel. Oh, wait a minute. Right? So, no, I don't. Just a moment. Now, b can also be represented as a half. Square root of b is the same as b to the half. This, since it's in front of the log, can multiply it, but then it can go in front, or sorry, as an exponent, like this. The log b and b cancel, and x to the half is indeed a square root of x. So prove it's true. We just did it. And this one is saying b to the 4 here, to the power of this, is equal to x squared. Okay, so this 4 is allowed to then jump up over here. We're allowed to then put it as an exponent. This log b and this b cancel out. X to the half, which is what a square root is, to the power of 4 is the 4 times that. 4 over 2 is x squared. So left is equal to right. And there you go. Hope that helped.